So good evening, everyone. I welcome you all to the third lecture of STEM's 2022 lecture series. Today, we are delighted to have Professor Vidit Nanda with us. Let me give you a brief introduction about him. He is an associate professor of mathematics at the University of Oxford and a fellow of Pembroke College. His research interests are at the interface of algebraic topology, geometry, and data science. He completed his PhD from Rutgers University and was a postdoctoral fellow at the University of Pennsylvania. He is also an SMRI visitor at the University of Sydney. Today, Professor Nanda will be delivering a very interesting talk on how algebraic topology helps in understanding the data present around us. Before we begin, just a couple of quick points. It would be great if everyone can turn on their videos so we reach closer to an in-person talk. And also, if you have any questions, you can put them in the chat or ask directly to the professor. And if you put in the chat, the moderators will voice them at the appropriate time. Without further delay, I invite Professor Vidit Nanda. I hope all of you enjoyed the talk.
Well, thank you everyone for being here on a Sunday evening. I don't think I spent a single Sunday when I was in high school attending mathematics lectures, so it's very nice that the rest of you are doing it. You're far ahead of where I was when I was at that stage. Let's just leave it there. So the title of my talk is Big Mathematics for Big Data, and I would like to say that this will not contain a lot of heavy details of the mathematics. I'm told that you have different experiences. Some of you may be in eighth, which is, I think, a little bit early to start unleashing the hardcore heavy mathematics on you right away. So we're just going to take it easy. This will be a relaxed talk. I just want you to take away some pictures from the talk. If you have any detailed questions, you can either email them to me or tweet them at me using the links at the bottom of this slide. If I get signed up for any suspicious email spam, then I will know who did it and I will come and find you. So don't do that. Right, with that being said, thank you so much to Amik and Anirudhan for the invitation to speak here. I was born in India, spent many happy years of my life in India, keep coming back, but I think this is the first time I'm giving a mathematics talk in India. It doesn't feel like in India because I'm in my home, but still, it's very nice to be in front of a home crowd. So let's get started. What does an average mathematics talk look like? Well, it looks like someone like me trying to explain a theorem. A theorem is one of these scary looking statements. I do not want you to read it necessarily. So this is the sort of thing that I would, if I was giving a research talk, spend an hour explaining every line, every word in that statement, what it means, what it is good for, and so on. And in case you thought I was joking, here's a bigger, scarier looking one. So these are, don't read it. I can see you reading it. There's no point. There's the scary words. So all of them have the same basic structure. It starts with a scary family of adjectives. Let this be a finite, regular, n-dimensional complex. Let that be a category equipped with so and so. So these are all assumptions. And they look scary if you haven't picked up the vocabulary yet. So we go to graduate school so we can go and figure out what all of these things mean, what all these words are. So we have a good starting point, a shared vocabulary. It's like learning a language. And then on top of that, there are some new devices that are being defined in the paper that has these theorems. And then those devices that you've defined have certain properties. So that's what a theorem looks like. This is the anatomy of a theorem. And those properties, again, are adjectives of the kind that you'd learn in graduate school. Fortunately for everyone here, I will not be talking about any theorems in this talk. This is about how the big machinery of mathematics can be used in data analysis. So as you're picking up this vocabulary, you're already starting to do it. You see trigonometry, you see calculus, you maybe see a little bit of linear algebra already in your school mathematics. And as you're acquiring it, this information, you start to get a sense of what's called mathematical taste. And this looks different for different people. In my case, I think it was most like this. I did not like large equations, and I love geometry. So much like Drake, I really enjoyed the study of shapes, the geometry and topology and things like that, which I will talk about. And I was extremely scared of big integrals or big derivatives or those God help you, what are those cosine of a plus b plus c? What has split this up into smaller things? So I wasn't very happy with those, but I really like geometry. So it's perfectly fine if your Drake is flipped and you really like these calculus and algebra and analysis, but don't like geometry so much. We all have our tastes. So you build your taste. And then the question is, what does all of this mathematical stuff have to do with data science? How do you analyze data using mathematics? And perhaps the simplest starting point is you just have two variables, two things that you can measure. We all have smartphones these days, so the two things we measure can be, how much exercise you got and how much time you wasted on YouTube that day. So that, exercise is on the x-axis, YouTube is on the y-axis. And I'm not putting labels here precisely because I want your imagination to do that for me. I mean, you put whatever you like on the x-axis and put whatever else you like on the y-axis. Okay, so now we have these two variables and we take a lot of measurements every day. You watch 3 hours of YouTube, you run for 2 minutes, right? So that is 2, 3, the point in the plane. And you do these measurements for a while and you get some cloud of points. And now it looks like the more time you waste on YouTube, the more guilty you are and the more exercise you do, which is probably good, right? It's a healthy way of living, I guess. So data science is all about taking these finite observations and building what's called a model, something that explains the relationship between the two variables, exercise and YouTube. And if you look at this for a little bit of time, you realize that it's sort of linear. It looks like a line going through the origin, through the point 0, 0. So that's of the form y equals ax, and there's some slope, and you really want to figure out what the best slope is. So if we choose y equals 0, that's the flat line. I don't think that's a good approximation to these points. If you choose x equals 0, that's the straight up line. That's you just spend all your time on YouTube and you have no idea what exercise is. That's also a terrible approximation to these data points. So what you really want is to use either calculus, so you take some derivatives, you solve an optimization problem, y equals ax plus b, you don't know what a and b are, so you make them variables, and then you try to find the best fit using, take a derivative of the distance to the line function from all of these points. Don't have to know how to do this, but I'm just saying there's a way using differential calculus, even though I have put an integral sign there, there's a way using differential calculus to optimally solve this problem and find the best line. If you like linear algebra, there's an equally good way using matrices. So you can define a projection to operator to the line and then try to find the best orthogonal projection. Again, you don't have to know what it is. It's something like this line, no matter which of the two, whether you like the algebra approach or you like the analysis approach, if you do it right, if you don't completely screw up the calculation, you will get something like this line. Now, what does one do when one has this best fit line? Well, now you have acquired superpowers. You're like Thor with the hammer, not without. So if someone gives you a new x point, let's say further out to the right than any of the points on the slide, and says, well, you did this much exercise. You did 3 hours of exercise today. How much YouTube did you watch? Well, none of the points you have are going to tell you this. The data points are not going to tell you because you don't have anything that far to the right in the x value. But you have the line that tells you how these points relate to each other. So you look at your point, you go up from that point. So maybe you are, let's see if we can do this. Maybe you are over here. You look up to the line, and then you go to the y, and that's how much YouTube you watched that day. So you have this power of prediction, which you did not have before, simply because you managed to collect a lot of data and fit a good, clever model to that data because you knew it was a line, you know the formula for a line, and then you just have to tweak around the parameters to find what the best line is out of all the possible lines. This is your introduction to a field of mathematics and statistics called linear regression. Regression means fitting data points, and linear means to align. So the whole thing just means fitting data points to align. This works really, really well for data that looks like it fits along a line or maybe a small dimensional subspace. So what happens when you try the same technique here? So imagine you collected your data points and it looked like this. On some days when you did no exercise, you watched no YouTube, very little YouTube. And on some days you did no exercise, you watched a lot of YouTube. So maybe some points cluster down here and other points cluster, up over here. So what do? What's the best line through these points? Well, I don't know about you, but I don't think any line that you draw, whether it's like this or like that or like this, is really telling you what's going on in this data set. What you really want is an ellipse, right? That runs tightly like this through the points. So, okay, you might have to go back and remember what the equation of an ellipse is. X squared over a squared plus blah, 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 something equals 1. I don't remember. Hopefully it's in one of your textbooks. So when you find that, you now need those other parameters, x squared over a squared plus y squared over b squared equals 1. So what are those a and b? And you can play exactly the same game that you did before. You do the calculus or you do the linear algebra to find the best a and b that fit the data points that you already have. And let's say you find it. So now you have two superpowers. You have Thor's hammer and you have Thor's bigger hammer. You have the line hammer that'll fit any line you like. And you have the what is that axe thing? Not Mjolnir, the other one, whatever. The axe thing that'll tell you the best ellipse through any data points. Great. So now you have two superpowers. And then Loki puts this data set in front of you, and now you're screwed because this is not a line, it's not an ellipse, it's something else. Well, now you have to go back, pick up another book, realize it's a parabola, and try and fit the best parabola to these data points, which you can do if you know the equation of a parabola and know which parameters you want to get this sort of juice out of. Okay, so now you're getting a little bit tired. You have a line, you have an ellipse, you can do a parabola, and then this data set comes in front of you. Okay, this is not any of those old things. This looks like a sine wave, but it's not quite a sine because it goes now. It's minus sine of x, right? That's what y looks like. It's negative sine of x, if you know what the function is. Okay, so what is the frequency of the sine wave? What's the amplitude? There are two other parameters, and then you have to do exactly the same game. But in all of these, the point I'm trying to make, I promise the rest of the talk will not be new shapes of data. The point is that you have to know what you're looking for before you can apply this regression tool. If you fit a line to this, it's going to be terrible. Even if you fit this line, it's going to be terrible if you go far out away from the origin. So what you need is a way to recognize what the shape of the data is before you start fitting parameters to it using regression or anything like that. And this is where algebraic topology plays a huge role in data science. So there were no problems when things were linear. When it was a line, the first slide worked. You just y equals ax plus b, and then you find the a and the b. All of these problems happen because the data is nonlinear. The function that's describing how x and y relate to each other is not a linear function. And this is where we get into a little bit of trouble. So we need a method for recognizing or quantifying non-linear shapes like this sine wave. So let's summarize this using one of my favorite stories from history. This is ancient, even before you were born. In fact, it's so ancient, it's before I was born. This is the story of Odysseus, who the Greeks had this big battle in Troy. Achilles fought. There have been movies made about it. I'm sure we've all read at least one of the stories of Achilles or someone. And so the Greek heroes, after having had this very long, very expensive, very sad war in Troy, are coming back home. And it's a mess. The journey back is not fun. And Odysseus is at the southern tip of this white space. He's the mainland of Italy is to the left, the shoe part of Italy. and the island of Sicily is to the right. So you're going from south to north, Italy to your left, Sicily to your right. And as their ship is going, there appears a monster to the left. This is the big monster Charybdis. It looks like a whirlpool. It has teeth. If your ship goes in there, it's and it just gets flushed down to the bottom. So don't want to go to the left. Okay, let's go to the right. On the right, there's an equally scary monster called Scylla. It's a snake thing with 6 heads. And so you're at the south, you have a big boat, and you have to decide whether to go to the left or to go to the right. And this is the problem every data scientist has in life. It's these same 2 monsters. On the left is nonlinearity. There's a whirlpool. It doesn't look like a nice line. It's just going to take your whole model down with it. And to the right is Scylla. It's 6 heads. It overfits by a factor of 6 here. So overfitting means, where there's very small deviations and your model tries to, go through all of them instead of building a straight line or something like that. And this is the if you run away from nonlinearity and make sure your model is linear, you'll get a bad fit. So what did Odysseus do? Well, he did not want to lose his whole ship. So he went to the right towards Scylla. So Scylla came, ate 6 of his favorite people, and then they escaped after that, after losing 6 people instead of losing the whole ship. That's the story. You can look it up. So that's what all the data scientists have been doing. They have been trying to fit, linear or almost linear models to all sorts of scary, complicated, nonlinear data. And then they lose. Sometimes the model doesn't predict things nicely. So we are going to take a different approach. We're not going to try and fit these nonlinear or linear models. We're going to try and understand the shape of the data first. And the way I want to do that is, as promised in the title, topology. Topology is not so easy to define, and I'll try and explain why it's not easy to define. But if you want the slogan, the one sentence definition is topology is what you get, ready, when you take geometry and subtract analysis. So take geometry, all the things you do, measure angles, what is it, trigonometry, sine of theta, blah, blah. You take all these angles and lengths. Those are the important things, right? What can you build with a compass and a ruler? Remember the 60 degrees and the 90 degrees and all of those? Okay, so you take all the geometry, but you rob yourself of the ability to measure lengths and angles, which sounds strange. It's like nothing is left. What do you have of geometry when you take away the metric, the ability to measure things? Well, it turns out that there's a lot left, but many people did not realize that. So this definition, topology equals geometry minus analysis, has been calculated to maximally annoy 3 different types of mathematicians. So I encourage you to use it in front of them. Nobody is happy about this definition because, topology looks like it's less than geometry. Analysis looks unhappy because there's a minus sign. Why are you taking me away? Geometry is unhappy because, all the tools that they love are just, taken and put in a box and they can't use them anymore. So yeah, no one's happy. Anyway, the reason, so this is difficult to even imagine what's left of geometry that we know and love if we take away measurement. And it is because of this reason that topology is one of the youngest branches of mathematics alive today. So if you think about geometry, we know the Babylonians were doing it. They have left us tablets from 2000 BC, which again is before I was born, surprisingly. It's just describing all of these, measurements that they took and all of this. This is ancient. Geometry is, I think, the oldest by far branch of mathematics. Number theory is slightly newer. It's 300 BC, and it goes back to the Greeks. Now, that's not a game of Connect 4. Those are the prime numbers that have been 2, 3, 5, and so on, if I haven't screwed up. So those are, that's number theory. Analysis, around the same time, the Greeks were measuring areas and volumes, not with calculus, but in their own way. So calculus and analysis, basically. Also, credit to the Greeks, 250 BC. And representing the home crowd, algebra was India and transmitted by the Arabs over to Europe. much after all of this, 850 AD. So it's a long time afterwards. Okay, compared to all this, where does topology come? 1735 is the birth of topology. So depending on whether you think that Euler did it first or Riemann, it's either 1735 or 1860. And look at the dates on the left and look at the dates on the right. There's an enormous difference in the birth dates. So topology is very, very young because it took a long time for mathematicians to realize that you could do geometry without measuring lengths and angles. So what is this birth of topology due to Euler? Well, Euler realized that if you take a sphere and chop it up into triangles, like imagine you have a football, like a soccer ball, it's full of pentagons and hexagons, but you can always make triangles out of them by subdividing them. So let's say you did that. And then I asked you to count the number of vertices minus the number of edges plus the number of triangles. What would you get? Well, it depends, right? How many vertices? You could always have a smaller, more refined triangulation. Well, it turns out the answer does not depend on the triangulation. It's always 2. So you can run an experiment. You can triangulate your football, and you can count the number of dots minus the number of lines plus the number of triangles, solid ones, and you always get 2, no matter how you triangulate. This is amazing. And this is the birth of topology. So something has to explain why we always get 2. And that explanation was given by Riemann many, 130 something years after this fact was discovered. So let me tell you how to solve this problem. How do we know that this is always going to give us 2 rather than, 15 or -7, because it could be negative, it could have lots of edges. So the reason the answer to this sum is always 2 is the following. So we take a line, and here we do 0, 1, 2, 3. So on top of 0, take all the vertices of your triangulation. So they're all sitting in this bin, and you make a vector space. What it mean by that is if you have 50 dots, 50 vertices, then you just make a 50-dimensional vector space. So fine, R to the 50. It consists of x0, x1, x2, all the way up to x49 or something. So that's 50-dimensional space. Take all the edges, put another vector space on them. Okay, now you know what the game is. Each edge has 2 vertices in its boundary. So connect them by a graph, right? Something like just connect each edge to the 2 things in its boundary. And there's no reason to stop at edges. You can look at a triangle and then you realize that each triangle has 3 edges in its boundary. And every tetrahedron, if you were allowed to go further, if you had a 3D solid football, would be connected to 4 of these triangles. And this game never ends. You just keep until you run out of triangles and tetrahedra and 5-dimensional things and 20-dimensional things, which I sort of cleverly have decided not to draw. So what happens is that these connections form matrices between the vector spaces. So you can take, these are called boundary operators because they take a cell, a simplex, this is what they're called, 0 simplices, 1 simplices, 2 and 3, and they connect each k-dimensional simplex to an appropriate number of k-1 dimensional simplices, which lie in its boundary. So you're just algebraically recording what is next to what. And this is called a chain complex. And the defining property is that if you compose 2 of these matrices, you get 0. So what that means is if you look at this triangle, you look at all the ways to get to edges in its boundary, and then you look at each of those edges, and then you'll go to 2 vertices. The vertices occur with plus and minus signs. So there will be 3 vertices on the right-hand side that these 3 edges go to, and each one will come with a plus and minus sign, and they'll cancel. And so the boundary of the boundary will be 0. That's the starting point of this entire field. And this discovery leads to the main hero of the story called homology. So the homology of the chain complex is the kernel of one of the matrices quotient out the image of the other. And the reason we can do that is when you compose 2, you get 0. So everything that del 2 can possibly produce is sent by del 1 to 0. So the question is that everything? Is everything del 1 sending to 0 produced by del 2 or not? And the answer is sometimes yes, sometimes no. So that difference is called the homology group of dimension 1. And this is called the Betti number, the dimension of this HK. And these have very nice geometric interpretations. So Betti 0 is counting the number of pieces. So if you had 2 footballs, then the Betti 0 would be 2. It is just counting how many pieces there are. No one cares about how you've triangulated them, how many vertices there are. It's going to be the same. It's a geometric feature. It has nothing to do with the triangles and lines, even though we use the triangles and lines to define it. It's independent of that. Betti 1 counts the number of loops, so it's sort of tunnels in your shape. And Betti 2 counts the number of cavities. So the football would have 1 because there's a bit. The difference between Betti 1 and Betti 2 basically is if you're an insect and it's a Betti 1 hole, you can fly out of it. It's a tunnel. If you are an insect inside a Betti 2 hole, you're dead because there's no way out. So it's completely enclosed. So it's a life or death matter. So you should know the difference between these two, I guess, if you're an insect. Okay, so this way you can keep going, even though I don't have a good way of describing these in terms of geometric pictures, because then you're in dimension 3 and 4. You can keep going, and when you run out of simplices, you also run out of Betti numbers. So it's 0 if there are no simplices of dimension large. Now, let's answer Euler's question. You can prove using basically the dimension of null spaces and so on. It's not so bad that the Euler characteristic is the alternating sum of the Betti numbers. So it's Betti 0 minus Betti 1 plus Betti 2 minus Betti 3, blah, blah, blah. And because the Betti numbers themselves do not depend on the triangulation, this alternating sum does not depend on how you triangulated anything. So this answers not only that the soccer ball Euler characteristic is 2. You can take any space like this and figure out what its Betti numbers are here. There are 2 connected components because there's there's a torus, like a tire, there's a sphere, and then there's a point. The point is disconnected from everything, so that's 2 connected components. The torus has these 2 loops that are not in the boundary of the second chain group, and similarly there are 2 cavities, one inside the sphere and one inside the torus. And so that's the 2, and there are no 3-dimensional anything or higher. And so if you take the alternating sum of these, you get 2. So now you have learned, this is your first introduction to homology. You're not supposed to get everything out of it, just a vague idea of what at least these Betti numbers are measuring. They're measuring pieces and different types of holes. So 0 for pieces, Betti 1 for a tunnel, Betti 2 for a void. If you remember that, you're in good shape. Wow, something has appeared on my screen.
Can you disable annotation? So on the top right of share screen, you'll see disable annotation.
Okay, let me do that.
Sorry about this.
No problem. Clear all drawings is the best I can do. I don't see a disable.
Okay.
Okay. All right. Well, if they that's unfortunate, but hopefully that there won't be too many others. Okay, so let's go on. So how does all of this help in understanding data? So let's go back to the beginning when we had this cloud of data points, and I'm not putting X and Y axes. Let's say this is a cloud of data points that someone has given you after taking measurements. And the question is, well, what is it? And you say, well, it's a cloud of data points. And I ask, okay, but where did it come from? And you say, I have no reason to figure out what this is. I mean, why should I know? And the last time I asked, I was giving this talk, version of this talk a long time ago, and I asked what this was, and someone said dead goat. So I've stopped asking people what it is. It's just too morbid. It's not a dead goat, I promise. So, so how would you try and figure out what this shape is? Well, one thing you can do is play connect the dots, right? So things that are very nearby, let's at least join them up to see if some structure emerges. Okay, now it's starting to look like something I've seen before. I'm not sure what it is. I'll tell you what, let's fill in some of these triangles. I promise you've seen it. It's very familiar. Wonder what it is. And if you keep playing this game, there is a chance, if you know what you're looking for, that someone will turn the lights on and you will know what the picture is. Now, this doesn't happen all the time, but when it happens, it's pretty special. It's great when you find what you're looking for in data just because you connected the nearby pieces at the right scales. The trouble is we don't quite know what the right scale is if someone doesn't already know what the final answer is, which is usually the case in data. So let's take a simpler data set. And I'm going to try and get rid of these annotations. How do I get rid of clear? Good. So what you can do is cover these with balls, right? You just grow thicker and thicker radii. This is what would happen if you looked at this and sort of crossed your eyes a little bit. Okay. Anyhow, so when we grow these balls around it, then this structure starts to emerge. We have lost some connected components. So if you look at the upper left, these used to be 3 points, and now they're only they're 1. They've joined up. So Betty 0 has dropped by at least 2, and so on. So what you can do is, as you thicken these data points that you had, you will see Betty numbers changing, the Betty 0, 1, and 2 changing. And as you thicken even more, then you will see the Bettys changing even more. So here you found like a Betty 1, because there's a tunnel that's been created because the loop is complete. And if you grow things up a bit more, then that loop will get filled in and the Betty 1 will disappear. So you can take all of this data and summarize it sort of nicely using a diagram that looks something like this. So for each Betty number, so let's say Betty 0 or Betty 1, you take the scale, how thick were the balls, or what was the radius when something was born, when a loop appeared, and what was the radius when that loop got filled in. So this is a birth on the x-axis, and there's a death on the y-axis. So just recording the radii at which something appeared and then disappeared. And so this is called a persistence diagram. And this is the object that people use in algebraic topology to study data. If you take any point, look at its distance from the diagonal, that tells you how, what fraction of how many scale values the feature persisted for. If you're very close to the diagonal, that means your birth and death are very close. That means you didn't live for very long. So it was just a little blip, right? You saw a little tunnel and then immediately it got filled in. Whereas if you're far away from the diagonal, it means, well, you were born at a very early stage, and then lots and lots and lots of thickening had to happen before you actually disappeared. So the things that are close to the diagonal are noise. There are things that, if you perturb things a little bit, they might disappear entirely. The things that are very far away are these Betty numbers that are stable, that will withstand all sorts of permutation. So formally, if you have a simplicial complex at each stage and you include one into the bigger one and bigger one, which is what we get by thickening these balls around the data points, you get a picture like this. So we start with the data points, and now we're just thickening. There's a radius going along the x-axis of this picture where things are getting bigger and bigger, and you're connecting things as they come within that sphere of influence of each other. So the beginning, everything is disconnected. And the blue lines at the bottom are Betty numbers. So 1, 2, 3, 4, 5, 6, 7, and 9. There's 9 points, so there should be 9 horizontal blue lines that are just counting things. When you get to the middle, some nearby things get connected. We lose a lot of Betty components, and so the blue lines are dying. You see them ending, these intervals ending early down here, over here. And then as you go towards the end, it just becomes one connected blob. And so there's only one blue line that is surviving for large for large radius values. Whereas the holes, well, this is Betty 1. This is the first time a Betty 1 is formed over here. And so this red line is capturing that. For a brief moment, there's two holes, and then they both get filled in, and that's the end of the game. So this is called a barcode. You get bars, and it's sort of capturing all of the homology groups that appear and disappear in your data point and on the upper left of the screen over time. Time being measured as the rate of inflation of the radius of the balls. And these are completely so what I'm saying is that the homologies are completely described by this simple combinatorial picture of barcodes, which is equivalent to the picture of the persistence diagram before. This is just if you see a bar from A to B, think of it as the point A comma B in the 2D persistence diagram, and everything lives above the diagonal because you have to be born before you can die. So hopefully that part makes sense. We're not doing karma and rebirth here. So it's just everything is on the upper end of the above the half line. Okay, good. So now, what is the property that makes this really, really nice for data analysis? It's called stability. So if you take these data points that we had in the beginning, you get a barcode. In each dimension, 0, 1, 2 of homology, you get a barcode. And now if you sneezed on these data points, if there was noise in your measurements, and if you were only certain of where that point was within some radius, then what happens on the right-hand side is that all the bars are allowed to move their endpoints by that exact same radius. So if you had a very, very tiny bar, like the one lower down, it could disappear completely, because if you move the endpoint on the left a little bit to the right, and the endpoint on the right a little bit to the left, they sort of collapse. There's no bar left. So the very tiny bars are unstable. Like I said, these are the points close to the diagonal. So they could, they may as well be on the diagonal. And these very long bars, even if I move their endpoints by a little bit, they remain long bars. So the long bars are the stable ones, and the short bars are the unstable ones. If you really want to describe a shape and not think about the noise that's coming from lots of little tiny data points and their fluctuations, you just want to keep track of the longest bars in this barcode. So this sort of analysis has had impact in many, many fields of science and engineering, and I want to give you 3 examples. And I'd give them in order of increasing complexity. So new breast cancer was discovered just by keeping track of the Betty 0 barcode. And the way they did it was they looked at a data set that contained lots of tumor data, and they looked at Betty 0, and they realized there was a big gap somewhere. It looked disconnected. So it looked like there were 2 different families of tumors. And then they realized that something on one of the arms had been mischaracterized by scientists and engineers, and realized that it went over there. And that was a new kind of breast cancer. This is work of Gunnar Carlson and Monica Nicolau and Arnold Levine from 2003 or something. It's been a while. The other one is dimension 1 and 0. So this uses dimension 1 exactly, I think. So Betty 1 is used here. And here's the problem. You have a region like this square, and there are lots of little robot sensors that are guarding it. And you want to know if someone could escape detection, if a thief could be hiding, not seen by one of these robot sensors. And if you look at this picture, the answer is of course, right? There's all these blank white spots where there's no, I could be over here, this pencil could be over here, and then okay, it's great. No one, I can escape. But if the robots are moving, then you kind of have to dodge them, and maybe you'll get trapped. Now it's a really hard problem. Is there a path across time for someone to not be seen by any of the robots when they're moving? And this coverage criterion has a very nice homological solution due to Vin De Silva and Robert Greist. This is from 2005 or so. And the one I'm going to talk a little bit more about is dimension 2 and 1. So this is dimension strictly less than 3, which is the study of protein compressibility. So let's talk about that one a little bit more. So here's a protein molecule. its compressibility is exactly what you think it is. You apply some pressure and measure the change in volume. And if you like differential equations, remember I did this like Drake when I saw a differential equation. But if you like differential equations, this is what it looks like. So the thing on the left is compressibility, and on the right is the rate of change of logarithm of volume by with respect to pressure as you keep the temperature fixed. So this is what people like to measure. It's an important physical property of protein molecules. It's a very expensive thing to measure precisely because you have to sort of freeze the protein in place and then run this expensive experiment. You have to take a single molecule and then crush it. So it costs an enormous amount of money to actually compute this in practice. And I think out of the several thousand proteins known, compressibilities have been measured only for about 50 of them or so right now. So it's not easy to do. Let's say you wanted to predict what compressibility was using only the data of what the atoms were and where they were. So here's a typical protein atom, protein molecule. It looks like this. So the old school telephone wires, I don't know if you recognize them because you're too young, but the rotating things are telephone wire type things. These are called alpha helices, and the thin strands connecting them are called beta sheets. And so every protein molecule is basically a backbone of carbon atoms. And those carbon atoms, C4, so it has valence 4. So on the left and right, it's connected to other carbon atoms. But the two other valences are allowed to connect to anything else they like. So sometimes they pick up oxygen, sometimes they pick up nitrogen. And those oxygens and nitrogens like each other. And so the thing folds into some complicated 3D shape because the other things attracted to the carbon are also attracted to each other. So instead of being a straight line with things sticking out, this oxygen over here really wants to talk to that hydrogen far away, so it folds. So this is a 3D folded protein, and it's not difficult to measure what these locations are and what the atoms are. So this is from the protein data bank. So you can just forget the first few columns. On the right, you see starting from the middle, the X and the Y and the Z coordinates, and on the absolute right, you see the oxygen, carbon, nitrogen, carbon, carbon. So this is what the data looks like. And so the question is, if I just give you data like this, no differential equation, can you tell me how compressible a protein is? It sounds ridiculous. How could you? You haven't measured anything. And amazingly, you can. So let's start with the following. We will just build balls around the protein atoms the way we talked about before. We know what the locations are. We know what distances are, so we'll grow balls. And the first thing we're going to do is if we see something like this, you have the ball of, the big ball is for the very attractive atoms. So maybe it's an oxygen, and the little ones are for, let's say, carbons. So if you thicken this a little bit, what happens is that the hole in the middle disappears, right? So this is like a noisy Betty 1 is what that looks like. So we want to discard things like this. This is not going to play any role in compressibility. The second one is if you have Betty, the picture on the left, things are very tight. That's not going to be very compressible. The thing on the left is not compressible. The thing on the right is, because the distances between the atoms are more. You can squish the thing on the right a lot more than you can squish the thing on the left. So here we're going to make a rule that if and what's the difference between these two in terms of the barcode? Well, there's going to be a bar that starts very early on the left, right? You just thicken the atoms a little bit and bam, you find the loop. There's a tunnel that a fly can go through. So that's a Betty 1. On the right, you have to thicken those a lot before the tunnel forms. If the black dots are close, if the radii are small, then you're not going to get a tunnel. You're just going to get 5 pieces or whatever number of points there are. So that's the other consideration. We want to filter things so that they're born late. And finally, this requires a little bit of geometric insight. If you have a long tunnel like this, then each Betty 1, so you have a tunnel, and that's giving you Betty 1. As you thicken it more, it gets pinched at the parts where it's undulating. Remember, the alpha helices are sort of, they undulate. So each Betty 1 is going to, in this case, the Betty 1 is going to lead to 3 Betty 2s. So each of these 3 sort of peanut shapes is going to become its own Betty 2, even though it used to be a single Betty 1. If this thing was 1/3 as big, it would create only 1. So the ratio of Betty 2 to Betty 1 is sort of a proxy for the length of tunnels. We cannot measure this in practice because it requires sort of angstrom level measurements with very sophisticated devices. So this is a rude calculation, right? Just Betty 2 over Betty 1 is probably correlated well with high compressibility. So take the one-dimensional persistence, the diagram, take the two-dimensional persistence diagram with the birth and the death axes and all of that. The first thing we do is filter out noise. So take a threshold, everything within that distance of the diagonal is noise, and we kill it. Then take the lower and upper bounds on how big the starting and ending points have to be for the points. And everything that lies in that region between L2 and U2, but at least delta away from the diagonal, is important based on the geometric pictures. So here's a conjectural definition. It's the number of points in the 2D persistence in that range divided by the number of points in the 1D persistence on that range. And of course, I haven't told you what L1, U1, L2, U2 are. So for some L1, L2, U2, and delta. And when we did this, using regression to find the best L1, L2, this is the measurement we got. These are real proteins, real compressibilities measured along the x-axis, and our prediction is along the y-axis. So here's a nice fit over here, and these three are a terrible fit. These three do not fit at all. And so when we looked, these two BUW and A4V were measured at 25 degrees instead of 0 degrees. So they don't count. And 1E7I, I think, is hemoglobin, which is the only protein to have iron in it. So it does not quite have the same properties as the others. So if you throw away these three, that are, two of them are at a different temperature from all the others, and one of them is a very different protein anyway, you get a really nice straight line fit. So we can predict compressibility of most proteins without doing any expensive experiments. Okay, so hopefully you get at least a flavor of how algebraic topology is being used for real scientific things, despite being this very abstract branch of, geometry minus analysis, just this topology. And I don't want you to get the feeling that this is the only branch of mathematics that has been making contributions to data science. There's so much out there. There's so many amazing things. And so I won't be able to go into detail into any of those because I don't have that much time left. And but let me tell you three that I really love very quickly in just icon form. So here's my first favorite one. If you look at a graph, there are ways you can sort of. So imagine that this graph is a very complicated algorithm that you want to run, and you want to split it among different processors. It's too big to do on a single machine, so you want to split it among two different cores of your computer or two different computers in a big cluster. So what you want to do, and these, each node is a computation and each edge is a dependency. So if two nodes are connected by an edge, then the result of one computation is needed before you can do the other one. So if you have a computation described like this as a graph, what you want to do is partition it. You want to split it into pieces that are roughly the same size, and you can send each piece to a single core. And what you want to do is split as few edges as possible when you partition it, because the more edges you split across different cores, the more you have to communicate across cores, and that's expensive. So how do you take a large, complicated computation graph and split it into the right number of pieces that are roughly the same size while disconnecting as few edges as possible? And the answer is you look at what's called the graph Laplacian. This is a matrix defined of n by n, where n is the number of vertices here. And this graph Laplacian has what are called eigenvalues and eigenfunctions. You take a small eigenfunction corresponding to an eigenvector, rather, corresponding to, let's say, lambda 1, and then wherever that is positive, you call one piece. Wherever that is negative, you call another piece. And that automatically bipartitions you into roughly equal sized graphs. It's amazing. And the theory of eigenvectors, or in more generality, eigenfunctions of the Laplacian, is a huge area of research in actual sort of hardcore mathematics, whether it's PDEs or harmonic analysis or all of these functional analysis, it shows up everywhere. My second favorite problem is if you ever look at stock prices, they form these very noisy time series data. So if you have a terminal which is telling you the Sensex or whatever at whatever day, then it looks like this. And so these are called time series. And if you have lots of them, you might want to figure out how well they're correlated with each other. If iron goes up today, does the Geo share price drop? Something like this. You want correlations of this type. And what you can do is take a whole bunch of these, and these form a path. If you take 5 of them, they're going to give you a path in 5-dimensional space. And you take this path and you integrate it on a simplex, which is 0 less than x, less than y, less than z, less than 1, something like that, along all possible dx, dy, dz's. Like just permute those. And it's not going to split into a triple integral because it's over a simplex and not a cube. So these all have different meanings, different measurements when you perturb them. And this sequence of numbers almost completely characterizes the paths, and you can feed it into a machine learning thing to just give you a vector that very accurately summarizes the path, and then you can learn what all of the correlations are. So this is called iterated integrals for obvious reasons. There's 3 integrals there. You can do more. And the invariant you get is called the path signature if you want to Google something later. So path signature machine learning will bring up everything about this that you want. And the third one is a very, very deep story. It's called sheaf theory. And this is in fact what I used in the first theorem on the first slide that I then said I will not say anything about. So I won't tell you anything else. But if you look up sheaf theory and data analysis, the work of Robert Greist and all of his collaborators, you will find something interesting there. So this is Google homework for you if you're interested. I'm not going to collect it. I'm definitely not going to mark it. So it's for you. It's not for me. So we've gone through a lot. It's been a long Sunday. So I want to end with something refreshing. And usually it's a cup of something delightful. And when I'm speaking to mathematicians, this is usually coffee with the foam on top, the milk at the bottom, and the coffee at the. But given the crowd, let's say this is masala chai with cream at the top, milk in the middle, and then these tea leaves at the bottom. And this is my picture, my mental model for all of mathematics. Right at the top where the cream is are the applications. This is where you get to interface with other scientists, other engineers, interact with them like we did with biologists when trying to figure out this protein compressibility problem. You have to learn something new about their domain before you can make any contributions to it. Underneath that layer, the milk, is where we do computations. Nothing we do is useful to scientists unless you can crunch a large amount of data. And you need efficient algorithms to do it. So computational mathematicians sort of support that layer. They're underneath, handing away tools to the very, very applied people, so that if you want a quick, fast Fourier transform, you don't have to code it from scratch. It's already in some Python library somewhere, written by some nerd who has, a lot of time to come up with these great, clever tricks in computing things. Underneath that are the people like me who are studying the theory. They're just trying to, make things that are designed for let X be an infinite space. And then you're saying, okay, what happens if it's finite? Can I put it on a computer? Can I just express things in some finitary way that will become useful to some nerd doing computations, that will become useful to some other nerd talking to a biologist? And what happens, you may not realize this at a very early stage in your life, what happens is you very quickly start, find your level in this masala chai, and you just live there. If you're a theoretician, you just talk to other friends who are theoreticians doing abstract stuff. If you're a computational guy, you just talk to other people doing algorithms. If you are interested in applications, you just become a biological, mathematical biologist. What we need in this masala chai to make it exciting is a little bit of vertical movement. So if you're super theoretical, you should talk to someone upstairs doing computation. See if the stuff you've just proved can be put on a damn computer. If you spend all your time with algorithms, see if someone needs them. That's usually nice. You will get a lot of cred if your algorithm is being used by an actual scientist to solve an actual problem. Similarly, also talk to theoreticians. There might be new things that you can compute that they have been working on. So as you grow, as you become mathematicians, please, please talk, look around you for people at a different height in this teacup. And that's where all the excitement is. Okay, I've taken enough of your time. Thank you so much. Here's my website if you want to get to the papers, and feel free to send me any questions now or later. I'm happy to answer them. Thanks for listening.
Thank you, Vidit. The talk was really amazing. So currently we will wait for some few minutes. So if people have any questions, they can ask it now. So Anand, you have a question?
Yeah, hi, Professor. Thank you for the talk. Really enjoyed it. I had a question about the how you define the compressibility in terms of like the persistent, like counting the points in the ranges on the persistence graphs. How do you like prove, or is there some basis for how it's equivalent to like that differential equation definition that you gave, like in terms of pressure and volume?
It's
right?
Absolutely not. So this is an empirical measurement. We are not proving this is right. So we're not proving that this is going to give us the same number. All we are saying is anytime you have been able to compute that number, except those three cases, using this other method, we approximate you to within that band of that line that we have. It is entirely possible that somebody else is going to measure a new compressibility at 0 degrees of a perfectly normal protein molecule that will not be on our line. Then we have to refine our model and say, explain why that thing. And that's science. It's not mathematics anymore. So there's no proof there, except the fact that this measurement using only this ratio of points that is completely cheap to do, that you can do in your bedroom today, is giving you very similar results to something that requires thousands and thousands of dollars in government investment to measure in a lab. That's the achievement, not an equivalence with the differential equation.
Okay, thank you, Professor.
Mm-hmm.
So I have a question, like what was the name of that graph technique that allows you to split computations between nodes?
Spectral graph theory. So look up spectral graph theory. There's a whole book on it. There's probably several books on it. And also look up Fiedler eigenvector, Fiedler eigenvector. And you can definitely email these questions to me, because anything I write will probably be more sensible than anything I'm saying now. But yeah, spectral graph theory.
Yeah, I mean, like, is there more like a Python package for that kind of thing?
Oh, many.
Okay.
Many. So look up. So these days, I think the what you want is the METIS library, METIS, to split your large. I'm assuming you have a terribly, enormously, annoyingly large graph that you really want to split. So METIS, METIS.
Okay, like it's not small. It's like pretty small, but like it's a special case of that kind of problem.
Okay.
So, like,
Yeah.
not very large. So yeah, but I think it could still work. Yeah.
Good.
Thanks.
Mm-hmm. Anything else? Why are there 6 things in the chat? Should I be reading those?
No, that's fine. There are no questions right now.
No questions.
If you have any question, you can also send by email later on.
Exactly. Yes.
And do follow Vidit on Twitter. He puts a lot of good stuff there.
There is one mathematical fact for every 5 jokes. That's my goal. That's the gold standard. 5 jokes per one mathematical tweet.
Hello.
Ishan, you have question?
Yes, sir.
Yeah, go ahead.
Sir, I have no question from here, but a question which I stuck. Can I tell?
Sure.
Sir, x to the power minus x to the power x is equal to 2 to the power 2. Then solve x, sir.
Is it okay? I think there is some not very non-related question right now.
Yes.
Yeah, we can.
I strongly recommend stackexchange.com. that is where I would put this question. And then somebody with lots of time just attacks it and solve it, probably take logs of both sides. I don't know.
Yeah. So I think we can come to a conclusion now. So thank you, Vidit, for your exciting talk. It was really amazing how you started with some memes and story of facades, and how you also told the history of topology. And it was also quite interesting to see that this homologies can be also represented by barcodes. It was really that, yeah, it was a cool fact. And also, yeah, like I'm pretty sure people like would be motivated to study algebraic topology by the implications, how you should it
Yes.
breast cancer discovery and
I
all this robotic sensor. Yeah, it was quite nice.
I have not just on Twitter, but also on my webpage. I teach computational algebraic topology every year at Oxford. And I have this long set of lecture notes full of pictures like this one. So if you're interested, just download those, go through them. If you have questions, attack me on email or Twitter as usual. So yeah, this was fun. I thank you for having me.
And yeah, definitely, I should thank you for the final piece of advice of moving vertically in the Masala Chai. I think that everyone should keep them, and it was, yeah, it was quite nice of an advice. So I think we can come to a conclusion. So thank you, Vidit, once again for accepting our invitation and giving a talk on Sunday morning. It was really wonderful to have you. So as Vidit also said, we will about a time series model. We have one lecture by Professor Sayar Karmakar on 6th of November, where he will talk about more on this time series model and other models of econometric computations. You should definitely attend that talk. And we will meet next on 24th of October, next Sunday. With the talk will be by Professor Rajesh Gopakumar of ICTS, where he will be talking about string theory. So we will hope to meet you next time. And thank you, Vidit, once again.
Thank you. Bye-bye.
Thanks a lot, Vidit. Amazing session.